So hello and welcome everyone. My name is Jayadal Sani, and in this video we are going to do the post-contest analysis of Weekly Coding Contest 193. So I hope you guys have done the best in the weekly contest, and so write down how many questions you were able to solve in the comment section below. Okay, so without wasting any further time, let's start with the first question, and the first question was minimum operations. So let's read out what this question is trying to say. So in this question, you are given a string S of even length containing lowercase and uppercase English characters. In one operation, you can change any character in S to any other lowercase or uppercase English character. Your task is to determine the minimum number of operations required to modify this string such that each letter in S forms a distinct pair with its opposite case letter. Okay, so what it is trying to say? It is trying to say that your task is to determine the minimum number of operations required to modify this string such that each letter in S forms a distinct pair with its opposite case letter. Means in a pair there should be a lowercase alphabet and there should be an opposite uppercase alphabet of that same alphabet of that pair. Okay, so let's try to see what are the distinct pairs we can form for this given one. So in this one we have A, B and uppercase B and A. So in this one, let's try to see if the string is, let's say, A, B, capital B, or let's uppercase B and uppercase A. So now it is saying that you can change any character. You can pick any character and convert it into whatever character you like, whether it be uppercase or lowercase character. So if we see how many pairs can we form over here, we can see there is a lowercase A and that can be paired with an uppercase A, which is already there. And the other pair that can be formed is lowercase b and an uppercase b. So in this one, I can see for this given characters, we can form distinct pairs and there is no operations required on any of the characters. So the output, the minimum number of operations required for this given string is 0. Now let's take a few more examples. Let's say the string str equals to a, b, c, and let's say the other string is a, b and b. So now what I'll be doing, I'll be trying out how many valid pairs already exist in the given string. So I'm giving you the intuition by solving out some of the test cases. So pay attention over here. So in this one, first of all, I'm finding out how many valid pairs are already existing in the given string. So here I can see there is a small case A and corresponding to it, there's an uppercase A as well. Now I want to form a pair for this lowercase b. So I have a lowercase b and an uppercase b. So they form a distinct pair. But what about this C and B? So if I want to form one more pair, I have to convert either this lowercase c or this uppercase b. So what I can do, I can apply an operation of converting this lowercase b to let's say uppercase c. So I can form third pair that is distinct and it is a valid pair. So here how many operations did I apply? I have applied only one operation, converting the uppercase b to an uppercase c. So now in this case, what I was trying to do basically, I was trying to first of all find out how many pairs exist. So I will try to find out what are the count of valid pairs that are already existing in the given string. So the count of valid pairs that were already existing was 2. Now let's try to find out how many total pairs can we form with the given string. So the given string will be of an even length. There will be even characters in the given string. So basically tell me, if you have even characters, then how many pairs can be formed with the even characters? So if we see if there are even characters, then if we know that the length of this string is n, then we can form n divided by 2, total number of valid pairs according to the problem statement. So if you want to know the total number of operations that we applied, can you pay attention to what is this total pairs? How many total pairs can we form? We can form, the length of the string is 6. 6 divided by 2 gives us 3. So total pairs that are possible is 3. And how many valid pairs are already existing? There are 2 valid pairs already existing. So if we want to find out the minimum number of operation, or let's say minimum operation count, is nothing but the total pairs possible with the given string. And let me just take it over here and write it over here. So total pairs minus the valid pairs which are already existing in the given string. Okay, so in order to find out the valid pair, we can directly use the formula length of this string divided by 2, and we'll get the this is for total pairs. Now in order to find out valid pairs, now let's see how can we find out the count of valid pairs. Okay, so in this case, in order to find out the total count of valid pairs, what I'll be doing, I'll be keeping the track of all the characters frequency. So I'll be creating a frequency array. You can create a frequency array, or you can also create a hash map of frequencies for uppercase as well as lowercase. So I'll take this same example and explain how the logic to find the valid pairs can be written down. So here, how many uppercase? Let's say here is the frequency count for, let's say, the lowercase, and there will be a frequency count for the lowercase. So this is the frequency count of lowercase characters, and there is the frequency count of uppercase characters. So if we try to see how many lowercase characters are there, A is occurring how many times? Once. B is occurring how many times? Once. C is occurring how many times? Once. Now in uppercase, A is occurring how many times? Once. B is occurring how many times? Twice. So now in this case, what I can observe, this is the frequency count. Now what I will be trying to do in order to find out a valid pair, I'll be iterating over the frequency count of all the lowercase characters that are already present. And what I'll be doing, I'll be finding out, let's say for this lowercase alphabet, let's iterate over the frequency count of all the lowercase alphabets. So I can see the lowercase character A has a frequency count of 1. Now I will try to find out what is the uppercase character of A, that is uppercase A, and how many uppercase characters are possible. So I can see that there is only one uppercase character. So if you take that, if you see that how many contribution, how many pairs will this lowercase a and uppercase A will contribute to the total count of valid pairs. So let's say there is some counter variable called as valid pairs. How many valid pairs are already there in the given string? So in this case, I want to know what is the contribution of this pair in the total valid pairs. So you can just take the minimum frequency of the lowercase character A and uppercase character A. So now I am using the term minimum over here. So why am I doing so minimum? Why am I doing minimum frequency of A or frequency of uppercase A? Because if you see, if you take some another example, okay, so I'll give you an example why I'm taking this minimum count, minimum frequency of uppercase and lowercase. But for now, imagine that I have taken minimum count. So what I'll be doing, I'll be taking the minimum count. So what is the minimum frequency over here? I can see this is 1 and this is 1. So minimum will be 1. So it will be contributing one pair to the valid pairs that are already existing. Now let's move to the next lowercase alphabet which is present, that is B. Now let's find out how many valid pairs will character B give us. So here is the frequency count of B, lowercase b, and here's the frequency count of uppercase B. Okay, so now here is the time where you will be understanding why I have taken minimum. So you can observe that there is a lowercase b, a single b, and there are two uppercase b. So now tell me how many valid pairs exist over here, distinct pairs. So this uppercase b cannot be used twice, okay? Or let's say this lowercase b cannot be used in two different pairs. You cannot create a pair something like this. It is not a valid pair. So from this I can observe that there is only one possibility, there is only one pair. And what is this one pair? What is this one? One is the frequency count of this B. So that's why I'm taking minimum over here. So for this B, it will be contributing 1 to the total count of valid pairs. Now moving forward, now let's see how many pairs can this C form. So now what you can observe over here, C is occurring once. But can you observe any uppercase C? No, the frequency count of uppercase C is 0. So now tell me how many pairs will be found by this lowercase c and uppercase c? 0 pairs, right? Because you have only lowercase c, but you don't have any uppercase c. So the frequency count of a number, or let's say of a character that does not exist in uppercase, you can take it as 0. So I'll take the lowercase c frequency count as 1 and uppercase C frequency count is 0. So the minimum of 1 and 0 is going to be 0. So this C will be contributing 0 to this count of valid pairs. Now in this manner, I have got the total count of valid pairs that are already existing in the given string. Now I'll find out how many total pairs can be constructed with the given string. So total pairs is basically length of the string divided by 2. So length of the string in this case is 6 divided by 2 equals to 3. So now if I want to know the minimum number of operations, we have already seen the formula. It is nothing but total pairs 3 minus valid pairs. How many valid pairs do we have? 1 plus 1 is equivalent to 2. So the minimum number of operations that I need to perform for the given string is equivalent to 1. So in this manner, you can find out how many minimum operations are required. Okay, so you can try out with different test cases and follow up this approach. So the basic idea is how many valid pairs are already existing, subtracting that count from total pairs that will be possible for the given string of length n. Okay, so this is the entire logic. Total pairs minus valid pairs. Okay, so now let's see the implementation of the same. So in order to implement this, what I have done, I have written the intuition as well. So I have implemented this code in Java, but it will be very much easy to implement in other languages as well. So number of operations is nothing but total pairs minus valid pairs existing in this string. Total pair is nothing but n divided by 2, and valid pairs which are existing in this string, you need to count from the frequency of characters. I've iterated over the length of this string and get the value of n. Now I have created a frequency array. You can create a hash map as well, but I thought of creating a frequency array for lowercase characters and uppercase characters. Then I'm iterating over the given input string and counting how many frequencies of every character exist. Then I'm interested in counting the valid pairs, right? So for counting the valid pairs, I have used a variable called as count. Now I'm iterating over all the possible lowercase characters. Now what I'm doing, I'm just checking whether this character, I'm just converting this index into some character by adding the ASCII value of lowercase a. So I'll get a character. Then I'm finding out the uppercase character by using some inbuilt method that will convert the lowercase to an uppercase character. Then what I'm doing, let's see how many valid pairs this lowercase character can form. So it will be nothing but minimum of the frequency of lowercase character or frequency of uppercase character, and you will be adding this to your counter. So this will be helping us to get the valid pairs, and at the end you just need to subtract the total pairs minus valid pairs. So n by 2 minus count will give you the answer. Now let's try to submit and see, and we can see that the problem has been successfully submitted. So this was pretty easy problem, and the intuition was not that difficult to analyze, but how you will be implementing and finding out valid pair was a little bit intuitive. Like you need to analyze that what will be useful to get the count of valid pairs. Okay, so now let's move to the next question. Count pairs. You are given two integers x and y. The task is to determine the number of valid pairs a and b such that a and b will be equal to x and a XOR b will be equal to y. If no such pair exists, then return -1. Otherwise, return the number of valid pairs a and b. So this question is going to test your understanding of bit manipulation and the bitwise operators that are used in bit manipulation. So let's try to see and understand how we can solve this question. So I've written down a very easy approach of this question, and I'll also give you some advanced, or let's say very observed, or let's say very intuitive approach in which I will use the properties of bit manipulation to get the same thing done with few lines of code. So these three examples are very important to understand how this a and b and how this a XOR b will help you to get the answer. So we'll be analyzing all these first three examples and seeing how this entire thing is working. So before going forward, let's have a look at the constraint as well. So x and y will be in the range 0 and less than 2 to the power 31. So integer will suffice. We don't need more than 32 bits to represent any number. Now let's move and understand what was the first example. In the first example, x was equal to 10 and y was equal to 1. So what is the definition of x? X is nothing but a and b. And what is the definition of y according to the question? It is a XOR b. So in the first example, when x was 10 and y was equal to 1, so let's write down, this is the binary representation of 10, and the valid pairs that the question has given in the explanation part is 10, 11 and 11, 10. So in all the answers, if you observe that if you can generate a single pair, then if you swap A and B, you can generate one more pair. Okay. So now let's say to see the bit manipulation that is being done on this. So A is equal to 10 and B equals to 11. If you do the AND operation, we know AND basically says 1 and 0 is equal to 0. Both the bits needs to be set so that we get the ith bit set in A and B. So this is 0, this will be 1, this is 0 and this will be 1. So 1 0 1 0, that's what we need, 10. So this is 10. This is the value of x. Now let's try to see the same thing in case of A XOR B. So we are expecting 1 over here, y equals to 1 in this case. So what happens in case of XOR? 0 XOR 1 will be 1, 1 XOR 0 will be 1, but 1 XOR 1 will be a 0 and 0 XOR 0 will be a 0. So in short, the XOR gives you a set bit when the total count of set bit will be odd. Okay, so now let's see the output over here. So here 0 XOR 1 will be a 0, this will be 0, this will 0 XOR 1 will be 1, then you have 1 XOR 1 0, 0 XOR 0 0, 1 XOR 1 you have a 0. So for this given 10, 11, you are getting the required x and y. That is, when you do A and B, you get 10, and when you do X or B, you get 1. Okay, so you can generate the another pair by swapping A and B. So you just need to find out two numbers, first of all, A and B, and then the second number can be generated by just swapping them. Okay, now coming to this second example which was given to us, where the output was 4. So what is the difference between the first and the second example? X was earlier 10 and Y was earlier 1. Right? X is 10 over here, Y is 1. And when you change X with 1 and Y with 10, the output changes. You don't get the same output. And obviously, because the meaning of X and Y is completely different over here. X is AND of two numbers and Y is XOR of two numbers. So the output that was given to us was 1 and 11. That was one of the valid pair, and the another valid pair was 3, 9. So the second pair can be generated, as I mentioned, by swapping the numbers. So in total, 4 pairs were possible. Now let's see the bit manipulation that is being done over here. So this is 1. Let's take A as 1 and B as 11. So when you do the AND operation, so this one and 1 will be giving you a 1, 0. For this one 0, for this one also a 0. So you get the output as 11. That's what we need over here. X was equal to 11. And let's see the XOR operation. So 1 XOR 1 will be giving you a 0. 0 XOR 1 will be giving you a 1. 0 XOR 0 will be giving you a 0. 0 XOR 1 will be giving you a 1. So here, what output do we get? We get 10 as the output, and that's what we need. So 1, 11 is a valid pair. So we can get 11, 1 by swapping A and B. Now let's say to see for 3, 9. Or let's say 9, 3. So I'll take A as 3 and B as 9. And here also A as 3 and B as 9, obviously. So let's see the AND operation of here. So AND operation will be giving you a 1 over here. Okay. Okay, so here it was a 1. My bad, it was not 11. So A and B will be giving you a 1. And if you do the XOR operation of both these elements, it will be giving you a 10. So this 9, 3 or 3, 9 is a valid pair. So in total, you are getting 4 pairs that suffice X and Y. So the output in this case was 4. Now the next observation is very important. The third example. Third example says X equals to 7 and Y equals to 10, where the output was actually -1. Now I'm starting the intuition along with this. So X equals to 7 and Y was equivalent to 10, right? So what is the binary representation of 7? It is 0, 1, 1 and 1. What is the binary representation of 10? It is 1, 0, 1 and 0. So in this case, what I can observe is that it is saying the output is not possible. But let's say to see why the output is not possible. So this will teach you that for what value of X and what value of Y, the output is not possible. So we know that X is nothing but 7. It is basically A and B. And here Y is equivalent to 10, and this is nothing but A XOR B. So what do we need in the XOR operation? We need 1 0 1 0. And over here, what do we need? We need 0 1 1 and 1. Okay. So now I'll try to generate the numbers A and B. Let's try to see if it is possible or not. And we'll be understanding why is it not possible to get any output. So tell me, so I have 4 bits. Okay, let's imagine that this number that we are going to generate is of 4 bits. Because we cannot show all the 32 bits, right? So starting with this position. Now tell me what bit should be there at this position in A and B. You'll be saying both the bits should be set bit. Then and only then you will be getting 1, or let's say set bit at this ith position. But if you keep both the bits set at this position, what will happen in the XOR operation? If you see, the XOR operation says that when 1 XOR 1 is done, you will be getting the output as 0. 1 XOR 1 gives you output 0. So this is working fine. So you can say that, okay, this ith bit will be set in A and B. Now let's see and move to the next bit. So next bit over here is 1. So both the bits should be set bit. So if you could keep both the bits set over here, now there is a contradicting assumption that we made. If you keep both this bit, or let's say ith bit set in A and B, then we know that A XOR, or let's say 1 XOR 1 will never give you a 1. It will always give you a 0. So now due to this reason that the same ith bit is set in X and Y, it is not possible to generate any kind of number. Okay, if you need ith bit set in X and ith bit set in Y, then there is no pair existing which suffice the A and B equals to X and A XOR B equals to Y. I hope it is making sense to everyone. So I am saying that if you have any overlapping bits, if you have any overlapping set bits in X and Y, then it is not possible to generate any kind of number. So how can we validate? How can we find out whether there is some overlapping set bits in X and Y? So in order to find out if there is any overlapping set bits in X and Y, it's very simple. If you want to know the overlapping set bits, you can just do an AND operation of X and Y. So if you do the AND operation of X and Y, and if this results into a non-zero, then answer is always -1. As we can see in 7 and 10. So 7 is 0, 1, 1 and 10 is 1, 0, 1, 0. So here you can see there is an overlapping set bit in X and Y, and that's the reason we are getting the result as non-zero. It is not equal to 0. So one observation that came to my mind, that in the beginning itself, so I'll be writing down few points and we'll be simultaneously writing down the solution, that if X and Y, if this is equivalent to, let's say, non-zero, then answer is always -1. Okay, then answer will always be -1. Then how can we generate the numbers? Okay, then how can we generate the numbers? So for what if X and Y will be giving you a 0? Then how many pairs are possible? So let's try to take this second example where your X was equal to 1 and Y was equivalent to 10. And let's try to generate the numbers. Assume that you don't know the answer. Okay. Now you should be focusing on the problem statement. That problem statement is interested into getting the count of possible pairs. They are not interested into generating all the pairs. Okay, fine. So I know that X is equivalent to 1. So this means that the AND operation of the numbers that I'll be generating should be 1. So A is over here and B is over here. And A is over here, the same A and the same B, and Y gives you 10. So now let's try to find out the count of numbers. So this will be 1, 0, 1 and 0. So what I can do, I can find out what bits will be possible at ith position by iterating over the bits of X and iterating over the bits of Y, doing this same thing together. So if you iterate over the bits of X, let's go and observe for X. For X, we can see this ith bit is set bit. So both the bits needs to be set in that number. So imagine that you are generating a number and that number is of 4 bits because I have used only 4 bits to represent X and Y as well. And that 4 bits will be this bits. So for the first bit, we know that this bit is fixed and it needs to be a 1. And let's check whether if the bit is set in A and B and the XOR will give you a 0 or not. Yes, 1 XOR 1 will give you a 0. So this bit, if you fix it with 1, it is fine. Now let's move to the next bit. So the next bit in X is 0. So now tell me when the output of AND will be 0. So 1 and 0 will be a 0. 0 and 1 will be a 0, or 0 and 0 will be a 0. So here there are two different possibilities. If you keep a 1, then this bit should be a 0 in B. If you keep a 0, then this bit can be a 0 or it can be a 1. But now let's validate whether it is sufficing over here as well. So I'm saying that if it is 1, it needs to be a 0, and if it is a 0, it needs to be a 1. So yes, this will be resulting as a set bit in this position as well. So now here I have two possibilities. I can keep a set bit or an unset bit for this position. So there are two possibilities for this position. For this position, this is fixed. Now moving to the next representation, next bit position, this is 0. So again, if I see a 0 over here, so again you will say you can keep a 0, a 1 or 0, and 0 or 1 over here. But now let's validate whether it will be valid for this case, 1 or 0 or 0 or 1. So when you do so, 1 or 0 will be giving you a 1, and 0 and 1 will be giving you a 0. So this means that you cannot have the assumption that you made that you can have a 1 or a 0 at this position. So what do we need at this position? So at this position, in order to get the ith bit unset in Y, you need both the bits to be 0 or both the bits to be 1. You need both the bits to be 0 or both the bits to be 1. Same implies over here. You will say that you need both the bits to be 1 or both the bits to be 0. The same thing will be there in this side as well, right? Because A and B are same both the sides. But if you see at this position X, if you keep both X and Y same, if you keep both of them and if you keep both the ith bit set, then the result of AND operation will be a 1. So this means that this bit cannot be set at this position. It needs to be unset. So this means that this position needs to be unset. Fine. So you don't have 1 over here, and this bit is also set, means it is fixed, and you can have only a 0 fixed bit at this position. So this is also fixed. Okay, I hope it is making sense, guys. So I'm trying to find out what possibilities can we have at ith position in A and B. Okay, in the number that we are able to generate. Now let's see A and B. Now this last position. So here again we have a 0. You will say we can either have a 1 or a 0, and we have a 0 or a 1. And if you do the same thing over here, if you have a 1 or a 0, and if you have a 0 or a 1, then will you be able to get a set bit over here? Yes, absolutely. So this means that in this position of the number that we are trying to generate, we can have two bits. There are two possibilities. You can generate a number by keeping a 1 at this position or a 0 at this position. So we have two possibilities. So for all the 4 positions, I have calculated what are the different positions. What are the positions where I can have either 0 or a 1, and all the positions where I can have a fixed bit, that is a set bit. Okay, so how many numbers can we generate? So here you are supposed to find out what are the positions where you can have either 0 or a 1. So the count of positions where you can have a 0 or 1 in this temporary representation is 2. There are 2 positions, right? There are 2 positions where you can have either 0 or a 1. So now how many numbers can you generate? How many different numbers can you generate with the help of this? So I'm writing down the numbers that we can generate. So I'll select for this position a 1, then I'll select a 0. I'm generating A for now. And here I'll be selecting a 1 and then a 1. Now in order to generate a B, we know that for this position, if it is a set bit, then in B it should be unset bit, right? So this is fixed. So these positions are already fixed. So I'll write down with white color. Okay. Now what about this bit? What should be this bit? If this bit is 1, this bit needs to be a 0. Then and only then you will get the output, right? Then and only then you will be getting 0, 0, 1 as the output. 0, 0, 0, 1. That is A and B will be giving you 1. And if you see the same thing over here, if you do the XOR of this, A XOR B, let's see what do we get. 1 XOR 1 is 1, this is 0, this is 1, and this is also 0. And that's what we need, right? 1 and X was equivalent to 1 and Y was equivalent to 10. Okay, so bear with me guys, this is very interesting problem. Okay, so I'm able to generate one pair, that is, this is what? This is equivalent to 11 and this is equivalent to 1. So one pair has been generated, 11 and 1. And as I mentioned, you can swap them to generate one more number. Now let's try to see another possibilities. So generating another number A and B. So the fixed bits are 0, 0 and 1, 1. And we know the output should be this. And here the output should be this. Okay, so earlier we have seen, I have selected a 1 at this position, so I'll go with a 0. And you know that if you select a 0, then this bit needs to be a 1 so that you can get 0. Okay, so wherever you have two possibilities, if you keep a set bit at this position, then you will take unset and vice versa. Okay, and this is out of this, so let me place it at correct positions. Okay, so now let's see what can we have at this position. You have already selected 1. Now you will go with a 0. If you go with a 0, then you need absolutely 1 over here, or you can go with a 0 as well. But if you go with a 0, then here you will not get a 1. Okay, so 0 and 0 is not possible. So 0 or 1 is possible, or 1 or 0 is only possible. Now the same bits will be there over here. So 0 and 1 will be there, and 0 and 1 will be there. Now what is this number? This is 1, and this is what? This is again 11, this is 1, and this is again 11. So we have again came back to this position, 1, 11 and 11, 1. So now what are the other numbers? It was saying for x equals to 1 and y equals to 10. They were saying 4 numbers were there, 3 and 9. Let's see how can we generate 3 and 9. So let's keep this aside. So I'll erase this because we have again reached back to 1 and 11. Okay, so now I need to generate some other number. Okay, so the other possibilities, what I can do is I can keep a set bit over here, and I will go with a 0 bit over here because I've already gone with a 1. So if I go with a 1, I'll get the same 11, 1 and 1, 11. So I'll go with a 0 now. I've selected a 1 over here, and I'll go with a 0 over here. Now at this position we know it needs to be a 0, and here also you cannot keep a 0. If you keep a 0, then 0 and 0 will not give you a 1. You definitely need a 1 over here. So I'm just showing you how the numbers are generated, and I'll combine everything to generate the final logic at the end. And here this will be 1, 0. So now what is this number? So this is 9 and 3, 9 and 3. So this is 9 and 3, and this is 9 and 3. Now we can swap the numbers and generate more numbers. So how many combinations are possible? In short, we are trying to find out combinations. How many combinations will be possible? So there are two positions, this and this, where here I can have a 0 and a 1, and here also I can have a 0, 1 and 0. So how many different numbers can you generate if you have two positions and you can keep a 1 or a 0 and 1 or a 0? You will say you have two possibilities, so you will multiply 2 twice to generate all the different possibilities, right? So this will be 2 into 2. So this means that you have to find out all the positions where you can have either 0 or a 1 in this temporary number. So if you are able to find out all the positions where you can have a 0 or a 1, then you can just multiply 2 that many times, or 2 to the power count will be your answer. 2 to the power count will be your answer. Okay. So are there any corner test cases? Yes, definitely. There are some corner test cases. So I'll explain those corner test cases while doing this thing, while iterating over this entire code, or let's say going through the entire code. So let's move to the code implementation. So before moving to the code implementation, I would like to summarize the entire algorithm. So the entire algorithm says if the result of x and y, if this is not equal to 0, then answer is always -1. That means there are some overlapping set bits in x and y, and this will not be able to generate any number. And if this is not the case, then you are supposed to find out the count, or let's say the positions where you can have 0 or 1. Means two possibilities are there at ith position. Let's keep it as count, and in that case your answer will be 2 to the power count. Okay, now let's move to the implementation. So what I have done, now first of all, forget about this thing. What I have done, forget about this thing. So if x and y is greater than 0, then written -1. So this is one of the corner test case which I have handled over here. Now let's try to see what are the different positions. So this answer variable gives you an idea about the position where you have either 0 or 1. So what I have done, I have iterated over x and y, and I am trying to find out whether xth or let's say ith bit is set in x or not. If this bit is set, in x, it has to be set in both a and b. It has to be set, means this bit is going to be fixed. That's what we have seen over here, no? When we have x equals to 1, we know that this bit is 1. That means this bit is going to be fixed. It has to be 1 and 1 or set in both the positions. Okay, so this is a fixed position. Then I am doing a right shift in order to move to the next bit of a and b. Okay, so I have done a right shift over here. Now let's say, imagine that this bit is not set in x. Now I will try to find out whether this bit is set in y or not. So y basically says, let's say if we come to this bit is set. So if this bit is set, I have found a position where you can have either 0 or a 1. So I will increment my count or answer variable. Okay, now what if the ith position in y is unset? If the ith position in y is unset, then that means it would have been unset in this as well, in x as well. Why? Because if you see, if ith bit is unset in x, then only then this part will be executing. So that means in ith position x, or let's say in x, ith position is unset, and similarly here, due to this condition, we have concluded that ith position in yth is also unset. That means again one fixed position has been found. So I will not increment my answer. But if we have ith position set in y, then I am incrementing my answer. And again, this keeps on happening until x is exhausted or y is exhausted. And at the end, you just need to do 2 to the power answer or 2 to the power counter, and you will get the answer. But that's not it. There is one corner test case which we need to handle. Now let's imagine x equals to 10 and y equals to 0. So in this case, what will be the output? Let's say if you have x equals to 10 and y equals to 0, means it is saying that let's say not 10 or let's say 7, all bits will be set, right, in x. So it is saying that all bits are set. 3 bits are there in 7 and all bits are set. That means a and b will be having all these 3 bits set. And y is equivalent to 0. Y is equivalent to 0. So what will be the answer in this case? If you have x equals to 7 and y equals to 0, means if your y equals to 0, then what will be the output? Let's try to see. So you are saying x equals to 1, 1, 1. Let's try to go and generate a and b. So you need both the bits set in order to get the output. So a, b, 1, 1, 1, 1, 1, 1. And what will be the XOR of it? Obviously it will be 0. So how many pairs will be possible? You have came to know that all the bits have fixed value. There are no possibilities at any position. Right? So the counter of positions where you can have 2 possibilities is 0. And there will be only one number existing. That is what? It is either 7, 0 or yes, only 7, 0 So that's what I have handled over here. If your y equals to 0, there is only one pair existing. So you can directly return a 0. I directly return a 1. But what if x equals to 0 and y equals to 10? In that case, we need to check. Why do we need to check? Let's see. What if x equals to 0 and y equals to 7? I'm saying that we need to validate. So let's say x equals to 0. So we know that a and b is over here. So all bits will be unset. And y equals to 7. This means that all the bits are going to be set over here. So how can we know? So I'll check this bit. So here you know that you can have both the bits 0 and 0. But here you know that you have to keep either a 0 or a 1 or a 1 or a 0. So here also you can do that same thing. So you have found one position where you can have two positions. You can have two possibilities. You can either keep a 0 or a 1 or 1 or a 0. Right? And again you will come over here. This bit is also again a set bit. So again 1 or a 0 or a 0 or a 1. So here also same thing, 1 or 0 or a 0 or a 1. And here also 1 or a 0 or a 0 or a 1. So you need to count. So what actually we need to count? We just need to count how many set bits are there in y. Okay, how many set bits are there in y, and just do 2 to the power position of set bits. How many set bits are there? That's it. Now let's say to submit it. And there is very easy way of doing the same thing as well. So this is a naive way of observing what can be the solution. Okay, I'll give you an easier way as well. So in the easier manner, what I can do is basically, in order to get the solution, let's once go through the solution. So this is very concise solution and it's very interesting solution. So you can do the same thing using the other approach which I have shown you as well. So what I am doing. So first of all, what is x? X is saying that a and b. So x gives you an idea about the bits which will be same in a and b. Okay, so if ith bit is set in x, then ith bit is going to be set in both a and b. Similarly, if we see what is y basically says that y is equal to a XOR b. So it gives you an idea. If ith bit is set in y, then that ith bit may be set in a and unset in b, or vice versa. Right? So it gives you an idea about the bits that differ in a and b. It gives you an idea about the bits that will differ in a and b. Okay. So what I will be doing, I will be trying to find out what is a. So assume that a gives you an idea about all the set bits in x and y. So if you do x or y, you will get to know about the set bits in x and the set bits in y. That will be a. So I am taking a as XOR of x and y. So you have all the set bits of x and all the set bits of y inside a. Now how can we find out b? Okay, so I have assumed that a is this. Okay, I have found the answer that let's say a is this. With the help of this, how can we find out b? So what is the formula of y? Y basically says that it is a XOR b. Now I want to find out the answer of b in terms of XOR. So I will apply XOR on both the sides. So applying XOR with y on both the sides. So this will give you a XOR b XOR y is equivalent to y XOR y. Now y XOR y will be 0. We know that, right? So what I can say here. So I want to find the answer of b. So I'll write down b separately and I'll put this a XOR y in a bracket. So this means that b XOR a XOR y will be 0. So therefore I can say that b will be equivalent to a XOR y, because if b and XOR of a XOR y will be 0, then b and a XOR y needs to be same. Then only then you can get a b. So I'll say b is nothing but a XOR y. You can use this operator or you can use this operator as well. Okay. Now I have found the value of a and b with the help of the properties of bit manipulation, that is XOR properties. And this is my a and b. Now I need to check. So this a and b, are satisfying the property of y as well. Okay, so basically I'm saying that when you do a XOR b, you will be getting y, but you don't know whether this a and b will give you x or not. So what I have done, in order to validate whether this a and b are correct or not, I have checked them whether a and b will be giving you x or not. If yes, then count how many set bits are there in y, and 2 to the power count of set bits will be the answer. If a and b is not equal to x, then your answer will be -1. So you cannot directly reach down and understand this approach if you have not gone through this entire thing. Okay, so this is little bit complex to understand, but after understanding that previous approach which I have shown you, a very simple approach, this might be easier. Okay, so this will also get accepted, and this does the task in constant amount of time, and the other approach that we wrote down was doing in log n amount of time. Okay, so it was taking some amount of time, but this will be doing the task in constant amount of time. So I hope you have understood this count pairs. Okay, so try to do the same thing. I have written the previous code, so try to go through the dry run of that previous code to understand it in a better manner. Okay, so now let's move to the next question, third question, that is string stack. So here you are given a string pet consisting of lowercase English characters, and you can construct a new string s by performing any one of the following operation for each character in pet. Means on every character of pet you are supposed to perform any of the given operations at least once. So what we can do, we can select an ith character and append it to the string s, or delete the last character of s. If s is empty, do nothing. After performing operations on every character of pet exactly once, your goal is to determine if it is possible to make the string s equal to the string tar or not. So what I'll do, I'll take the first example and understand. So this is very easy question. Okay, so the first one is saying that you have this as your pet and this as your tar. Let's try to see second example. First example of this question number 3. Name is string stack. So it is saying that the pet string contains G, A, U, A, and K, and the tar string contains G, E, and K. So with the help of the characters of pet, you are supposed to generate a string S which will be equivalent to tar. So there are two operations on ith character. We can append that ith character to S. Let's imagine the string str is the string that we will be generating. So let's go and apply all the operations on every characters. So str equals to, currently it is empty. Now I want to generate a string which is equivalent to tar. So I'm just supposed to return whether it is possible or not. That means return true or false. So now let's try to see. So in the tar string I can see G is present. So this G is useful. So what I will do, for this G I am going to append it to our string str. Now the next character is E, and here also I can observe that there is an E. So this E is helpful to us. So I will append it. I will not apply the delete operation. So if I summarize, ith character, we have two operations: append the character, ith character, or what you can do, you can delete the last character, of the string that you are generating. Moving on forward, what do we have here? We have U. Now in this case, what should we do? Should we insert U or not? So if we apply the delete operation for U, then this E will be deleted. But we know that inside tar we have 2 times E. So I should not be basically applying the delete operation, or else this E will be deleted and you will not get geek or the tar string in your str. So what I'll do, I'll append this U as it is. Now the next character is A. Now what I'll do, in order to generate geek, I don't need this U. So for this A, I will apply the delete operation. So that means U will be deleted, means the last character which was appended from this will be deleted. So one operation on A has been applied. Moving on forward, this is E. Now I can see that E is needed over here. So I'll append E over here, and the second character, last character is K. So K is also needed, so I'll append a key. So by applying operations, appending operation or deleting the last character of str on every characters, we are successfully able to generate the string str, which is equivalent to tar. Okay, fine. So how can we actually find out whether it is possible to generate str or not? So before, if you try to read the problem statement for the first time, it appears that okay, we are having two possibilities on every character: append ith character or delete the ith character. So you will be thinking about something similar to longest common subsequence, right? But here we don't need any longest, right? We already know the common subsequence that we need to find in pet. But you might be thinking about doing some recursion backtracking and trying out all the possibilities, but that is not at all required. So what is an easy way to do so? So the easier way is to think this approach, think this question in a different manner. So what basically we do when we see a problem, we start iterating from zeroth index to last index. But sometimes if we try to observe the solution in backwards manner, if we try to do it in a reverse manner, then sometimes we get a direct solution, which is very easy to implement as well. And a straightforward intuition is also observable. So now tell me what we should be doing. Let's try to see. Okay. So I will keep two pointers I and j over here. And I will try to find out whether all this tar can be generated, all the characters of tar can be generated from this pet or not. So I will do the iteration from right to left on both the strings. I points to k and j points to k in tar. I can see both the characters are equal. So when both the characters are equal, I am going to move both of them at the same time. Okay. Now moving on forward. Now I will be at A and j will be at this position. Now I can see that this I points to A and this j points to E. So this means that this A and E are not same. So if you have started the approach from left to right, then what would you have done? What we did when we analyzed this A? When we observed this A, do you remember that we applied the delete operation for A and the string str had GEU, and when A was observed, when we iterated from left to right on pet and A was observed, we deleted last character of str. So this delete operation says that you are deleting it. So how can we do the same when we are iterating from right to left? So in order to replicate the delete operation, what I will do, instead of moving the ith pointer only once, I want to apply a delete operation for this ith character in pet. So I'll move this ith pointer 2 steps forward instead of moving only 1 step forward. So this same left to right can be projected by doing an iteration from right to left, as we are moving I pointer 2 positions. When I find that I and j are not same, I will be moving the ith pointer to position. So I am saying that if pet of I is not equal to tar of j, pet of I is not equal to tar of j, in that case I will move the ith pointer 2 positions, minus because we are decreasing the value of I and j, right? So this delete operation can be reflected in this manner by moving ith pointer 2 times. Now I and j are similar, so move both of them at the same pace, 1 position, and now I can see both of them are putting in the same position, so move this j at this same pace. Okay, so it was working perfectly fine, and now this j has iterated over all the characters of tar. So I can observe j will be pointing to some index, negative index, and I can say, yes, we are able to generate tar with the help of characters of pet. So let's see a few more examples to get a clear understanding. So let's say the pet is G, E, and K, and the tar is basically geek, G, E, and K. I want to validate whether I can generate or not. And we know the logic: when it is not equal, I'll move 2 times. Now, first of all, let's go with this iteration right to left. I can see K k are equal, so I'll move this j pointer one step, I pointer one step. Now this e is also equal, so I'll move this j pointer one step and I pointer one step. Now this e is also equal, so I'll move I pointer one step and j pointer one step. And now at this position I can see I and j are not pointing to the exact same character. So what do you do? And basically you move I two steps, so I will be out of the range. Now we have exhausted all the characters of pet and we are not having any other characters that can help us to generate all characters of tar, because G is yet not generated. So for this, the output according to our approach comes out to be false. And that's exactly what you will be getting if you iterate and apply the normal, let's say normal process of the quotient from left to right. Let's see if we apply the normal process from left to right, are we able to generate tar or not? I'm showing you the same thing by doing from left to right iteration. Let's imagine you have str over here. So we have currently pointing to G. We need a G. I can observe G is there, so I'll generate a G. Now I need an E. Here also E is needed, so I'll append an E. Now I have an E. So I'll append E. I have an E over here, but now I need a K. So for this E, I'll use a delete operation. So if you use a delete operation, and operations are strictly to be applied on all the characters. So delete operation will delete this A. So now this str will have only E, and if we move forward, now we have K, so I'll use this K and append it to str. Now you can observe that GEK has been generated, which is not similar to tar. So you might be observing that in the beginning, when we did the operation, or let's say when we iterated according to our logic from right to left, the delete operation was observed on this E, right? And now we will be saying that, sir, delete operation has been observed at this E. Now how these approaches are same? So these approaches are same only because if you try out in a brute force manner, you can either apply the delete operation over here as well, you can either apply delete operation here also and here also. Okay, so imagine that you applied a delete operation over here, then this generated string would have been same like this only. So it doesn't matter whether you apply delete over here, here or here, but you will not be able to generate a string tar with the given characters of pet. Okay, so try it with few more examples. Try it with triple E and double E as your tar and pet. Okay, so you will get to know why is it working from left to right and how is it working from right to left. Now let's try to see the implementation. Implementation is very straightforward. Find the length of the first pet string as n and m as the tar length. I will be pointing to the last character of pet, j will be pointing to the last character of tar. While I and j, both of them are greater than 0 or equal to 0, I will check. If ith and jth character are equal, then move I and j pointer both together. Now if ith and jth character in pet and tar are non-equal, then you will move ith pointer 2 steps. And at the end, if j has iterated over all the characters of this star, then your value of j would have been less than 0. Right? As we have observed in this case, j was out of the range, right? J was out of the range. It was something negative. So this suggests that if j is less than 0, then answer is possible, else the answer will not be possible. Okay. Now let's try to submit it. And we can see that the problem has been successfully submitted. Okay. So we'll be moving to the next question. And the next question will be updated or uploaded as a part 2 of this entire video solution. Okay, so stay tuned for the next part 2 of this post contest analysis. If you really enjoyed this solution, then do hit the like button and share down your approaches in the comment section below. Okay, so that was it. Thank you everyone, and let's meet you in the part 2 of this post contest analysis. Thank you everyone.